3.2, what are solubility and concentration, from chapter 3? Concentration is a way to describe the amount of solute in solution. Concentration is listed in many different ways on products around the home and in industry. So grams per liter is the one we talk about most in our course here, and probably one that we could find around our house most often. Percent is another one that's quite common on household goods, specifically probably cleaning goods. And parts per million is used in a lot of water reports or on the news when they're talking about maybe contaminated water sources or air quality, things like that. So for example, let's calculate the concentration of a solution of sugar when 100 grams of sugar is dissolved in 1 liter of water. So what we're looking for here is a grams per liter unit. So we need to divide grams, 100 grams, by liters. So in the end, 100 grams divided by 1 liter, well, 100 divided by 1 is just 100. And the unit is grams per liter. Okay, so what this does mean is that there are 100 grams per 1 liter. That's what per some unit means. Let's calculate the concentration of a solution of salt when 360 grams of salt is dissolved in 3 liters of water. Again, we're looking for a grams per liter, so we're going to divide the grams, 360, by the 3 liters. 360 divided by 3 is 12 grams per liter, which again means 12 grams per 1 liter. Solubility is how easily and how much of a solute will dissolve in a solvent. To be insoluble means none or very, very little solute dissolves in the solvent. So little that it's like unnoticeable. So examples could be oil and water, they don't mix, or cinnamon in water. No matter how hard you try, you will not be able to get cinnamon to dissolve in water. Things that are soluble mean that some or lots of a solute will dissolve in solvent. Examples are sugar or salt in water. So let's take a look at the solubility of sodium chloride, potassium chlorate, and ammonium chloride in water as their temperatures increased. This investigation is on page 47 of your textbook, and it had a table of values, and I plotted those for you already in this graph. So a couple questions to go through. Are the graphed lines curved or straight? Well, we can see that this first one, blue, this represents sodium chloride, it says. This is a straight line. Potassium chlorate is this orange kind of curved line. So I would say that this one is curved, whereas this one was straight. And ammonium chloride is here, and I would assume that that is straight. So are the graphed lines curved or straight? Both. We see both types. As temperature increases, what happens to the lines? So as we move from left to right across our temperature here, let's look at our orange line. I see that the orange line increases. That means the solubility in water of potassium chlorate increases as the temperature increases. Same thing we could say with ammonium chloride. Its solubility in water increases as our temperature increases. Last one is sodium chloride. I would say that this increases very slightly. It hardly even moved in comparison to the solubilities of these guys. So as temperature increases, what happens to the lines? In general, they increase. So solubility in water increases. Which solute would you expect to have the highest solubility at 10 degrees Celsius? So I plotted 10 degrees Celsius here. At 10 degrees Celsius, the highest line is that of sodium chloride. At 40 degrees Celsius, it appears that sodium chloride is no longer the highest point. It is ammonium chloride. And at 100 degrees Celsius, we can see that the highest line here is still ammonium chloride. So these ones were plotted points that we actually could have tested in the lab, and then I put a line of best fit through them. I drew a line through those points. And I just kept extending it to 100 degrees Celsius because it's hard to measure in boiling water. Same thing with all of our lines. All right, so at 100 degrees Celsius, we said that it is still ammonium chloride. So in general, what happens to the solubility of a solute as the temperature increases? In general, as the temperature increases, the solubility of a solute increases. This could be seen in tea. If you make iced tea, it's hard to dissolve a lot of sugar in it. If you make hot tea, you can dissolve quite a bit of sugar in it. Try the experiment at home if you'd like. See how much sugar you can dissolve in hot or cold tea. So, some things don't dissolve in water. They were said to be insoluble. Grease and oil aren't soluble in water. They're insoluble in water. Insoluble in water. Sorry, I want to enunciate that for you. So how does our washing machine or dishwasher get rid of grease and oil? Well, we have to use soap. Soap has both a greasy and a water-soluble end. So lots of soap molecules surround the grease and allow it to dissolve in water. So let's go something like this. This is a molecule of soap. It has two ends. Let's say that this is our soluble end, and this is our insoluble end. And that's soluble in water or insoluble in water. All right. Now, our grease molecule, we know, is insoluble in water. So when soap is present, the soap molecules line up to put their insoluble end towards grease. So lots of soap molecules will surround our grease molecule. So much so that these soluble pieces are very close together. And then when the water molecules are surrounding it, it's okay because this end is soluble in water and the ends that are not are holding onto the grease molecule. So this whole particle now surrounded is now soluble. Okay. There is a little video here. To access this, just go to our general slides, and then you should be able to click on the link to go to this YouTube video on how does soap work. Or one of my personal favorites, I do love the Magic School Bus. Season 4, Episode 1, Meets Molecule, is a soap-fueled episode. So they talk all about how soap molecules will dissolve grease. A few practice questions for you to become a little bit more comfortable with the material.